Hello everybody, today we're going to talk about how to evaluate limits at infinity, and we're going to try to also determine the asymptotes of rational functions. First of all, let's first review what a rational function is. A rational function, r of x, is actually a fraction where the top function, let's say p of x, and the bottom function q of x are both polynomial. Okay. Again, a rational function is a fraction where the numerator and the denominator are both polynomial functions. Okay? And then let's try to talk about the degree of a polynomial, which is its highest power. So we need that concept, we need to review that concept to be able to determine the end behavior of the numerator and the denominator, so we can easily figure out the limit of this rational function as x approaches either infinity or negative infinity. So we can capitalize on it to evaluate the limits. All right. So whenever we have this rational function consisting of p of x over q of x, so we're going to end up with three cases. Okay. Those three cases are totally related to the highest power, highest degree of the top function and the bottom function. Okay, so number one, if the degree of numerator is equal to the degree of denominator, then the limit is the ratio of the coefficients of the highest degree. Okay, so if the degree of the p of x is equal to the degree of the q of x, then the limit of this rational function is going to be equal to the ratio of the leading coefficients. So when I say leading coefficients, they are the coefficients of the highest degree term. Okay. So let's say we have this as an example. Let's say example 1. Let's say we have limit x approaches infinity 4x cubed plus 3x squared over 5x cubed plus 1. So when you look at this function, so you can easily say that the top function and the bottom function are both polynomial. And also we can easily try to determine the highest degree of the top function, which is a cube, the highest degree of the bottom function, which is also a cube. In this case, we're going to draw the conclusion that they got the same degree. So that's why the limit of this function are going to be equal to the ratio of the leading coefficients. The leading coefficient of the top function is 4. The leading coefficient of the bottom function is 5, and this is the limit of this entire rational function. Okay, that's the first case. The second case, if the degree of numerator is bigger than degree of denominator, which means the numerator gets bigger and bigger, so it will become giant number. It will become giant number over number, which means this entire rational function is going to approximate to infinity as x approaches either infinity or in a positive infinity or negative infinity. So the second case, if the degree of the numerator is bigger than the degree of the denominator, then the limit is going to be equal to infinity. Okay, which means as x values get really large, y values approach infinity, which means the higher power will dominate the function. The higher power will dominate the limit of the function, let's say. Okay, and the third case, if the degree of the numerator is less than the degree of denominator, then the limit is going to be equal to 0, because the function is going to be equal to number over giant number. Basically, you're dividing top number by infinitely large number. Okay, and then the entire function is going to approximate to 0 as the limit of it. Okay, so as I told you, remember that we had three cases. The first case, if the degree of numerator is equal to the degree of denominator, then the limit is going to be equal to the ratio of the leading coefficients. Okay, and the second case, if the degree of numerator is less than the degree of denominator, then the limit is 0, because you're dividing a number by infinitely large number. Okay, that's why the limit is going to be equal to 0. And the limit of the let's say the degree of if the degree of numerator is bigger than the degree of denominator, then the limit is going to be equal to either infinity or negative infinity. Actually, that is depending on if x approaches infinity or negative infinity. So all I can say about finding the limits at infinity is totally dependent on the function that is dominating the entire function. Okay, the highest degree is going to dominate the entire function. Okay, so far we've talked about how to figure out the limits of functions involving infinity. So now let's try to talk about, actually before we talk about that, I would like to say that when you find the limit of any function as x approaches infinity, you're also finding the horizontal asymptote of that rational function, horizontal asymptote. Okay, so whatever comes out of this limit, that's going to be the horizontal asymptote. So in this case, the horizontal asymptote of this function is going to be equal to y equals 4/5. Okay, so this is very important. All right, let's move on to the next slide. And the next slide, we have some problems. In the first one, it says find the limits and the horizontal asymptotes. So basically, when we find the limits of all these functions as x approaches infinity or negative infinity, we would be also finding the horizontal asymptotes of these rational functions. Okay, so let's try to do the number one. It says limit n approaches infinity 4n squared over n squared plus 10,000n. And so in this case, the largest degree of this top function is 4n squared, which is the end behavior. Okay, and the largest degree of the bottom function is n squared, and this n squared is also our end behavior. And notice that we ended up with the same degree for top and the bottom. So which means limit of this expression is going to be equal to just the ratio of this leading coefficient. So 4n squared over n squared. These n squares are going to be gone, and the limit is going to be equal to just 4 for the first function. Since the limit is 4, that means this function, this rational function, has the horizontal asymptote at y equals 4. Okay. All right, let's move on to number 2. In number 2, again, the largest degree term of the top function is 2x. Also, 2x is our end behavior. So 2x over the largest degree of the bottom function is 3x squared. So which one has the highest degree? Which one is bigger, x or x squared? Apparently, the bottom function has the highest degree. So that's why, remember one of the cases, if the degree of the denominator is bigger than the degree of numerator, then the limit is going to be equal to just 0. So this function has horizontal asymptote at y equals 0. Okay, let's move on to number 3. In number 3, limit x approaches infinity, 2x to the 5th minus 7. So the end behavior of this top function is 2x to the 5th over the end behavior of the bottom function is negative 5x squared. So when you look at these two, you need to determine which one has the highest degree, or which one grows faster than the other. Okay, so in this case, apparently the top function is going to grow faster than the bottom function, so that's why the limit of this function will be infinity. Okay. Number 4, limit n approaches infinity, 7n to the 4th plus 500 over 3 to the power of n. All right. Apparently, the bottom of this rational function is gonna grow infinitely larger than the top function. So that's why this limit is gonna be equal to just 0, which means this rational function has horizontal asymptote at y equals 0. Okay, if the bottom function grows faster or bigger or larger than the top function, then the limit is going to be equal to just 0. If the top function grows faster, bigger, or larger than the bottom function, then the limit is going to be equal to either infinity or negative infinity. Okay, so number 5, limit x approaches negative infinity, 6 to the power of 1 over x. So in this case, I'm going to take a different approach to find the limit of this function. So what I mean is I'm going to plug in this negative infinity into this function, and let's see how it's going to turn out, okay? So let's do it. I'm going to do it over here, number 5. 6 to the power of 1 over negative infinity, okay? So we know that when you divide any number by infinitely large number, or infinitely large number, and it's going to be equal to just 0. The entire thing is going to approximate to 0. So that's why this top, in this different color, but this top is going to approximate to 0. And this expression is going to be equal to 6 to the power of 0. And when you raise any number to the 0 power, you're going to end up with always 1. So the limit of this function, this exponential function, is equal to 1, and then this exponential function has a horizontal asymptote at y equals 1. Horizontal asymptote at y equals 1. Okay? Let's move on to the next slide. In the next slide, we have these functions, these limits involving exponential functions, trigonometric functions, logarithmic functions, factorial. So in this case, what are we going to do? So what kind of approach should we take to find the limits of these functions as x approaches either infinity or negative infinity? So in this case, we have to look at this hierarchy. Okay, so there's a hierarchy among functions in terms of growing faster for increasing x value. So I'm just going to write down the hierarchy over here. So you need to pay extra attention to it, okay? So the hierarchy. So what is that hierarchy? So basically, let's say we have a constant number k. This constant number is going to be, then we're going to have logarithmic function, then we're going to have exponential function, okay? Actually, not exponential, I'm sorry, polynomial function. Then we're going to have b to the power of x, which is exponential function with the base of constant number. Then we're going to have factorial, x factorial. Then we're going to have another exponential function with the base of, with algebraic base, let's say. So basically, this hierarchy tells me that if I go from constant number all the way to the this x to the power of x, we're gonna see the growth rate. So basically, if I go from left to the right, so the functions are going to grow faster. So basically, if I give you an example, logarithm x is gonna have a faster growth rate than the constant number, or factorial is gonna have the less growth rate than the x to the power of x. So we're gonna take these hierarchy into consideration when we try to find the limits of functions at infinity. All right, so let's get started. And the first one, so we have, in the first part we have limit x approaches infinity x cubed over 1.01 to the power of x. So basically we have polynomial function on top, polynomial function, and on the bottom we have exponential function. So which one has the more growth rate? Okay, so which one is going to grow faster than the other? Apparently, according to this hierarchy, exponential function is going to grow faster than the polynomial function. So that's why denominator is going to grow faster than the numerator. So that's why this limit is going to be equal to 0. Okay, and as, in part B, we have constant number on the top, and then we have 5x and cosine x squared. So we have polynomial function and trigonometric function. So which one has the larger growth rate than the other one? Apparently, this polynomial function is going to have a larger growth rate than the constant number. So that's why this limit is going to be equal to just 0. And right here, limit x approaches infinity, ln x over 9th root of x. So basically, we can rewrite this expression as limit x approaches infinity ln x over x to the power of 1 over 9. So which means I just convert converted this ninth root into the polynomial. Okay, so which one has the larger rate? Okay, so which one grows faster, which one grows bigger? Apparently that according to this hierarchy, polynomial function is going to grow faster than the logarithmic function, so that's why the limit of this function will be just 0. Now let's continue. In part D we have limit x approaches infinity 100 to the power of x over x to the power of x. In this case, again, we have two exponential functions, but notice that one of them has a base of constant number, and another one has an algebraic base. So basically, apparently, algebraic base, exponential number with algebraic base is going to have a larger growth than the exponential functions with constant base. So that's why this denominator is going to get bigger and bigger infinitely. It's going to get infinitely bigger than the numerator, so that's why the limit of this expression will be just 0. Okay, and right here in part E, limit x approaches infinity x factorial over x to the power of x. So if I just take a look at the this hierarchy, so basically x to the power of x has the larger growth rate than the factorial function, which means this denominator is going to get bigger and bigger, infinitely bigger than the numerator, so that's why limit is going to be equal to just 0. The last one, in the last one we just turn upside down part E. Okay, so in this case we have limit x approaches infinity x to the power of x over x factorial, so which means in this case the numerator is going to get infinitely larger, which means it's going to become like a giant number divided by any kind of number. Okay, so when you divide any kind of giant number that you can think of divided by any number, the result is going to approximate to infinity. So that's why this limit is going to be equal to just infinity.